This is 2.9 Kinetics. There are 4 points here. The first is to recall how factors including concentration, pressure, temperature and catalyst affect the rate of a chemical reaction. The second is to use collision theory and the concept of activation energy to qualitatively explain how these factors affect the reaction rate. The third is to demonstrate a qualitative understanding of the Maxwell-Boltzmann distribution of molecular energies in gases and interpret curves for different temperatures and for catalyzed and uncatalyzed reactions. Then, finally, to relate the concept of activation energy to the Maxwell-Boltzmann distribution. So in chemical kinetics, reaction rate is the change of the amount of concentration of a reactant or product with respect to time. So before a chemical reaction can occur, the reacting particles must collide. After they collide, they may react. Whether they do or not depends on two factors. The first is that the reacting species must approach each other in the correct orientation, and the second is that they must have the activation energy, which is the minimum amount of energy required for the reaction to occur. So the rate of a chemical reaction can be affected by a number of factors: concentration, temperature, pressure in gases, and catalysis. So increasing the concentration of a reactant means that there are more particles in the same volume and so more successful collisions, which are collisions with at least the activation energy, and that will occur per unit time. This leads to an increased rate of reaction. Increasing the temperature means that the particles have more energy, and so more particles have greater than the activation energy. This again leads to more successful collisions per unit time. And increasing the pressure of a homogeneous gaseous reaction leads to the particles being forced into a smaller volume of space, which means you have more successful collisions per unit time. Now, catalyst is slightly different. It's a substance which increases the rate of a chemical reaction, but is not used up. And catalysts increase the rate of a chemical reaction by providing an alternative reaction pathway of lower activation energy. So you see on this diagram we have enthalpy on the y-axis and progress of the reaction on the x-axis. The reactants are here and the products are here. For a uncatalyzed reaction, you see that the activation energy is here, and for a catalyzed reaction, you see that the activation energy is lower. The enthalpy change, the overall energy given out in the reaction, is still the same, but the catalyst simply provides an alternative energy pathway. So for example, if we consider the reaction of calcium carbonate with hydrochloric acid, this is the equation. Calcium carbonate and hydrochloric acid gives us calcium chloride, carbon dioxide and water. Increasing the concentration of the hydrochloric acid means that there are more hydrogen ions in the same volume, and this leads to an increase in collisions with the calcium carbonate, so the reaction proceeds at a faster rate. So similarly, breaking the solid sodium carbonate into smaller pieces means more of the surface is available to react with the hydrogen ions, and this again leads to a faster rate of reaction. So in any system, the particles present will have a wide range of energies, and for gases, this can be shown in a graph called the Maxwell-Boltzmann distribution, which is a plot of the number of particles having each particular amount of energy. So the number of particles is on the y-axis and the energy is on the x-axis. And we see here where the activation energy is. So it can also be said that the area under the curve is a measure of the total number of particles present. So for a reaction to happen, particles must collide with energies equal to or greater than the activation energy for the reaction. And notice that the large majority of the particles don't have enough energy to react when they collide. Increasing the temperature shifts the curve lower and to the right, resulting in more gas particles having energy equal to or greater than the activation energy, leading to a faster reaction rate. So if a catalyst is used, the position of the activation shifts to the left, which has the same effect. So if we look at this graph, we have temperature 1 and then temperature 2, which is hotter. And we notice that the number of particles in the first case that have the activation energy is lower than those in the second case. So if a catalyst is used, the position of the activation energy of the curve shifts to the left, which results in more gas particles having energy greater than or equal to the activation energy, leading to a faster reaction rate. So you see here for an uncatalyzed reaction, and then underneath for a catalyzed reaction. So in this second case, there are extra molecules with enough energy to overcome the activation energy barrier.